Hello and welcome to my video, lesson 1.3 on geometric sequences. So just like a arithmetic sequence, a geometric sequence also has a pattern, but is multiplying, not adding. Okay, so we need to think about multiplying. So here we're multiplying by 3, multiplying by 3, multiplying by 3. We need to think about multiplying instead of adding. Okay. So how do we remember that? For me, I think about geometric as like geometry. Geometry is shapes, and you know what shapes have? Length and width and area. Length times width is our area. Multiplying is like area. It's the same thing. Multiplying and area are the same thing. And so they used to basically like only do multiplying and dividing and whatever with this idea of area in mind. Since then we have broadened our horizons in math, but it's actually easier to understand multiplication as area. And so that's basically what we're doing here as well. We're multiplying by 3, so we're just making areas over and over again out of the last direction. So it's kind of rotating the sphere, or the cube, and then making a new area. Rotating it, making a new area. Okay, so that is a possible geometric sequence. We talk about rate of change as well. So if you think about the number we're multiplying by is the rate of change. So if we think about any of our terms, so let's take 27, and you divide it by the previous term, that'd be 9, then we get 3, our rate of change. So that's all this is showing here. It's the rate of change of 3. Now, if we're going the other direction, we have to think about it the same way. This is not multiplying by 4. This is not dividing by 4. We need to think about it as 16 over 32, which simplifies to 1/4. What we're doing here is we're multiplying by 1/4. It's kind of like dividing by 4, but it is different because we're going to be using this rate. We're going to be using this rate here in order to get a general term. Just like we did with a arithmetic sequence, we're also going to be able to get a general term for a geometric sequence. So let's go ahead and try this out. If we think about T1, T2, T3, what do we actually have? All the way on to Tn. What do we have for T1? Well, we just call it T1. It's that simple. For T2, however, it's T1 times R, right? Times by whatever the rate is. T3, you can imagine, is T1 times R again. And actually, maybe let's put a couple more in here. Maybe we'll just one more. T4 is T1 times R times R times R. So we could actually simplify these to still T1 times R, but T1 times R squared, T1 times R cubed, and so forth. So if we put it as a general term, so Tn, we'd say T1 times R to the n minus 1, because you'll notice that our value here of 4 is dropped by 1 when we go to the exponent. All right? So even if you look at this first term, it also fits. It just has a r value of 0, the exponent to the r of 0. And this one has 1 of 1. So they all actually fit that rule. So we now have a general term for any term in a geometric sequence. So if I tell you a sequence, let's go with 4, 16, 32, ... and I want the give me the 11th term. This might be too big, but we'll try it. You can solve for it. So what are we going to do? We're going to go T11 equals T1, which is 4, times by, oh, and I made the R value also 4, so that probably wasn't the best plan of action, but that's okay. And then to the 10th. Okay, let's try this out. So 4 times 4 to the 10, it's going to be a big number. Okay, it's not too bad. Could be worse. So 4,194,304. Nice big number. I should probably not put the commas in there because that'll make it more confusing. Okay, so we were able to get it. Let's do one more example so you can pause the video, try it for yourself, and then go from there. So let's go with 3, 12, 36, 72, no, 100, 111, I think. Let's just quickly double check that on the other side here. No, 108. Made a mistake. All right. So please find term, and so this is another way we could show that. And then so I would go T 15. And so I want you to find T15. Okay, at this point it's a good chance for you to pause the video and try it out for yourself before I do it up at the front here on the screen. All right, so let's go ahead and solve this. So T15 equals 4, and then everything inside is times 3, times 3, times 3, whereas before we had times 4, times 4, times 4, right? So this would be times 3 to the n minus 1, so 15 minus 1 is 14. So let's see if we can try that out. So 4 times 3 to the 14. It might be too big. Oh no, we're good, we're good. So 19,131,876. All right. Okay, and our last question will be kind of different. I want you to figure out, find which term is I'm just trying to work backwards here in my brain. Find which term is the following term. So which number is it? Which n value? Okay, again, you could pause the video, try it out for yourself. Okay, so what you can do here to solve this is to plug in your value for the Tn. Okay, maybe I can zoom out a little bit so you can see the original red equation at the very top. T1 is 2. Times R is 2 as well, n minus 1. Okay, because we have the minus 1 and this one here, they'll actually add together to give us exactly 2 to the n. Okay, and there are a couple possibilities, but basically I'm going to tell you guys that we're only going to go with whole numbers here for n. So you can do a couple different things, but let's show one possibility, which is taking 1032 divided by 2 and working backwards to see how many times it fits in. Or you can just try a few things and see what works. So it'll be, so you can kind of like guess and check. 2 to the 10, let's see if that's too big or too small. So let's try that out. 2 to the 10. Oh. Did I make a mistake there? Shouldn't be 5. Oh yeah, I made a mistake. Oh my gosh. 24, 24. Should be in the same color. Ah. All right. So my bad. Should be in the same color. Okay, but I actually nailed it on my first try, so that's kind of a bad example. But you can go to whatever power, see if it's big enough, and then check another one, see if it's too big, and then go in between. So, anyways, that's the way we should have gotten to there. All right, another possibility is, I just mentioned this briefly in class, we could use logs, which I know that you guys don't know it at this point, but this is another possibility where we know that the log of a base answer equals the exponent. So if you can go log base 2 is going to give us this answer. What is the exponent? Well, let me show you how to write that in your calculator. If you click math and you go down to log base, it lets us put in whatever base we want, and we can type in our answer, and it gives us our exponent is 10. Okay, so logs are actually one way that we can solve for, or the proper way of solving for exponents. All right, so we went a little bit of a digression down here, but the rest of this stuff is all fair game, and I hope that this video helps you understand it a little bit better. Good luck.